So, okay, so here's an equation. And this is an equation that involves fractions. And you're certainly welcome to, if you feel comfortable, you can add or subtract the fractions to do the work and solve for x. But I think that's more work than you need. And certainly for me, that feels harder. So my goal here would be, I would like to eliminate these denominators. And the way we do that is we multiply both sides of the equation by something, right? And that something is actually called the least common denominator, but you can also focus on just something that's going to cancel out both of these or all of these denominators, right? So in this case, I'm going to multiply both sides by 10. The error a number of students make is they'll sometimes just multiply one side by one thing and one side by something different, and that doesn't work. That changes the equation and changes the solutions. This keeps the solutions the same because I'm doing the same thing to both sides. And what happens there is then I'm able to cancel as I distribute this. So in the first case, the 5 is going to cancel and it's going to leave me with a 2. So the 10 divided by 5 gives me a 2, and then I still have the 2x. And in the second case, everything here is going to cancel, right? The 10 is going to cancel with the 10, and that's just going to leave me with a 3. Here, the 10 gets multiplied by the x. And here, again, the 5 cancels with the 10, giving me a 2. So the other thing to be careful of is make sure you multiply every piece by 10, right? Not just the fractions, but every piece has to be the same thing. And what that does is it gives me an equivalent equation that's a lot better, right? This equation has no fractions in it. So it's certainly preferable, right, to our original equation. 4x plus 3 equals 10x minus 8. Subtract the 4x from both sides. Add the 8. Right, and then divide by 6. And I get 11/6. Does that answer the question? Is that a similar enough problem to what was done in the video?
No, yeah, that helped a lot. Yeah, I just got confused about like the 10 part and how exactly that functioned later in the equation, but I got it now.
Yeah, and this is a kind of an important thing about math is that a lot of times we get in trouble if we try and solve the problem directly. And it's much better for us if we can just make the problem easier and then easier and then easier until we finally feel comfortable to sort of solve it and finish it off. So in this case, this first step is really an important one to make the problem sort of easy enough that we then have a sort of routine way of solving it. So I would always encourage you, and I do this for algebra and college algebra and calculus courses, is if you have an equation with fractions, get rid of the fractions. It's just a good standard approach. Any other questions or topics? And again, when I'm working on these, feel free to jump in with the chat or just jump in and say something if there's a step you didn't see or understand. I'm happy to explain those a little more. I did want to talk. So this was an equation problem that we just did, which is good. That's one of our sections in the homework. There's also a couple sections on applications. We talked about this briefly, I believe last Wednesday. We talked about solving an application problem. But I want to go over a couple others just so we are sure we know the right kind of approach here. So example of an application problem. I'm going to do a mixture problem. So I think there are a couple of these in your homework. If you want 12 liters of a 40% salt solution, but only have 10% and 50% solutions available, how much of the 50% solution should you mix with the 10%? So this would be like a problem for a nursing student or a chemist, right? Where you have a certain solution that you're looking for, and you have to create it from two other solutions. Clearly, you want to mix some of the 50 with some of the 10, which is going to dilute it a little bit to get it down to 40, right? But the challenge is how much of each of those should we mix together to get to this 10%? Okay. So part of what we do when we work through this is going to solve this particular problem and mixture problems. But we also want to make sure that we are thinking in general terms, like, okay, how do I solve an application problem in general, right? Something that's maybe similar to this, or maybe very dissimilar to this, but still we can follow some of the same approaches. So the first thing that we want to do, of course, is make sure we understand the problem. And so that's what I was talking about. You know, we're going to mix some of the 50 and some of the 10 to make a certain amount, 12 liters of this 40% solution. So I have a rough idea of kind of what's going on with the mixing. So that's first, make sure you understand the problem. Number one, understand problem. Seems sort of obvious, right? But you'd be surprised how many times I run into students that have sort of not really thought about the problem and are trying to solve it. And of course, that's not going to end well, right? So number one is understand the problem. Sometimes a picture is helpful. Sometimes rereading it is all you need to do. Number two, we have to make sure that we define the variable. This is kind of, in my mind, the most important step here is we have to write down what is the unknown. And it's usually stated right in the problem. You usually don't actually have to look very hard for it, but you have to make an effort to write it down, or in some way indicate what the unknown thing is. So in this case, it's stated right in the problem. How much of the 50% solution should we mix? I mean, that's the question and that's the unknown, and that's what we want our variable to be. So I'm going to call that X. Okay. I don't know what it is exactly, but it's something, right? And that's the something I want to find. When we define those variables, we also would like to write the other unknowns in those terms. So what that means is we may have some other things that we don't know. We'd like to write those using X. I don't really want to introduce another variable unless I have to. What else don't I know in this problem that I'm sort of looking for? Anybody see something else that I would like to know to kind of finish this problem?
Liters.
So the liters is the measurement in which these things are. So X, to be specific, it is going to be the liters of the 50% solution. Right? Like I imagine I have two huge bins of 50% solution and 10% solution. So X is the amount of 50% solution I take out. What else do I need to kind of know to make my final mixture of this 40% solution? Anybody?
Any other unknowns?
Yeah.
40% and 10%? Yeah.
So I know that the final mixture is going to be 40%, but I sort of also don't really know how much of the 10% mixture I need, right? I need both of those together to make this other mixture. So I'd like to write this in terms of X. If I know my final mixture is 12 liters, and I have X liters of the 50% solution, the rest of it has to be the 10% solution. So we can write that as 12 minus X. Right? Like if X is 10 liters, then the 10% solution has to be 2 liters, right? 12 minus X. Whatever X is, 12 minus X is the amount of 10% solution. And I'm taking both of those together to get my 40% solution. So this is an example of another unknown that I'm writing using X. Those terms means like in terms of X. Okay, so I don't know it, but I now have an expression for it. Right? I have a way of writing it down. Okay, so the third step here, after I have the variables and the other unknowns, now I need an equation. A lot of times students try and jump to the equation part, and that's kind of where you'd like to be, but you have to do the work to get there. Okay, so we can't just jump there. But we can get there with a little bit of work. Now, this mixture problem, there's lots of different equations. I think we saw one with there's one with like a board on your take-home work, cutting a board into multiple pieces. And the equation there is pretty straightforward. It's like the whole board is equal to the sum of the pieces. Okay. This mixture problem is a little bit tricky because of what you have to set up as an equation. What we have to look at for the mixture problem is the amount of, in this case, salt in the mixture. So in our final mixture, we have 12 liters of mixture, but only 40% of that is salt because it's a 40% mixture. So 12 liters times 40% is 4.8. So that's how much salt I have in my final mixture. And that amount of salt has to come from my other two mixtures. Okay. So for each of those, I'm going to take the quantity times the percentage. And I have a 50% mixture and a 10% mixture. How much of the 50% mixture am I putting in? Like here it was 12 liters. How many liters of the 50% solution am I putting in? Well, and
I have a question.
yes,
How come we only put like 0.4 for 40 and 0.5 for 50?
oh, so, okay, they are actually, good question. They're actually, like, you can write them as 0.40 and 0.50 and 0.10. I don't know why I put the 0 on that one. It's not needed. The zeros on the end don't matter. It's only
Okay.
that number. So that was just, I don't know why. I don't have a
It's
good
fine.
answer. So
It's
that one,
something different.
yeah, well, and that's a good question because you don't know, right? Sometimes those things are important, right? The differences and intentional that I'm making. And in this case, they're not. So however you want to look at those, you're going to be okay either way. So remember, going back here, the amount of 50% solution, I don't know exactly the number, but I have an expression for it. I have a variable for it. It's X. So X times 50 or 0.50, that's going to give me the amount of salt from that solution, right? If it's 10 liters, 10 times 0.5 would be 5 liters. And that's how much salt would be in that mixture. And then I need to add to that the amount of the 10% solution. And I have an expression for that too. That's 12 minus X.
I have a question.
Yeah,
So you said that we have to multiply it by 40%, and this one was 50. The other one was 10, right? So I've been having a little bit confusion because of the point. So since it's a percentage, so where does the point come from?
yeah. So when we use percentages in equations, we want to use their decimal equivalent. So remember when you have a percentage like 50%, when you change that to a decimal, you move the decimal point 2 spots over. So if I had 2%, that would be equivalent to 0.02.
Okay.
Okay. So do you see how each of those is coming from just moving the decimal 2 spots over?
Yep, I see it.
Yep. And that's super important too, right?
Okay. Yeah.
So whenever you're dealing with percents in equations, we almost always want to write them as decimals.
Okay.
Yeah. Any other questions?
Nope.
Okay. Okay.
Sorry, can you just explain again super quick why it's 12 minus X?
Yeah, and I think when you're coming up with these, it's nice to sort of make a guess, like not like I'm actually trying to solve it, but just to imagine an actual number. So if X here is like 8, let's just say 8 liters, I want to get 12 liters total, right? So if I have 8 liters of 50% solution, then I have to have 4 liters of 10% solution, right? Because that gives me 12. And the way you're actually finding that is you're saying, okay, well, 12 minus 8, that's what gives me 4.
Okay, that makes sense.
And it's sort of hard to see, I think, when it's X, right? Like it's like, well, what is X? Well, it's just a number. I just don't happen to know it yet. So in the beginning, it's helpful to just imagine what number X might be. And then people are very good at sort of working things out. And then you can hopefully sort of repeat it and figure out maybe what the pattern or expression is, right, of that. Okay, because it's like you might know kind of what it is, but then this formula is a way of kind of checking it and saying like, okay, well, this actually works for different values of X. That's what I want. Okay. And these are all, steps to get us to this equation. And actually the equation here, this is actually, you guys will be good at the rest of this. It's setting up the equation that's hard. Once you find the equation, well, then we just want to solve it, right? And that's where we use our algebra skills. 0.1 times 12 is 1.2. 0.1 times X is 0.1X. You could get rid of the decimals by multiplying everything by 10 if you really don't like decimals, but I think these decimals are not too hard to work with myself. So 4.8 minus 1.2 is 3.6, and 0.5 minus 0.1 is 0.4. Divide both sides by 0.4. And that turns out to be 9. And that leads us to our 5th step, which is make sure that we answer the question. And I'll combine that. I'll say check. So you don't stop and say 9. You want to go back and make sure that you really answered what the question said. And you want to kind of check and say, like, is that answer reasonable? Is that possible? So I always go back to the problem and I say, okay, well, the question was asking how much of the 50% solution should we mix? And X was that amount. So that tells me that my answer should be, oops, I wrote it on there, 9 liters. It didn't ask me how much of the 10%, but some of these will ask you how much of the 10%. So if that was the case, I'd have to write down how much of the 10%, right, which is 3 liters. And then I also want to say, like, is that reasonable? Well, I mean, I don't know if that's the exact answer, but I mean, I do because I solved the equation and I feel confident with that. But I know I shouldn't have 12 liters of 50%, right? I got to have less than 12 of 50%. So some of 50 and some of 10. So 9 seems reasonable looking at it that way, right? If I got an answer like 27, I'd say, well, that doesn't make any sense, right? That's not possible. Something went wrong, right? And so that's what I'd like you to kind of look for with that check, that checking step. Right? Okay, did I really answer what was asked? And is my answer reasonable? I would much rather you say, do all the work and look at the answer and say, this answer, on a test or something, to say, okay, I don't know, something went wrong because this answer doesn't make sense. To me, that's a really good step. That shows you are thinking and know what you're trying to do with the problem. I'd rather have that than someone that just writes down an answer like 42 that has no chance of working. That doesn't look as good, right? So don't be afraid to sort of say, what's wrong. That's part of trying to solve problems, right? You don't want to pretend something is right when you know that it's not right. Okay, I know this is not a super easy word problem, and it's partly because of that mixture problem, but I do want you to focus on these steps, right?
I have a question.
Yes.
So you said if we were supposedly supposed to look for the leaders for 10%, how did you get 3 leaders? Is it from
Oh,
9?
yeah. So remember, I want a total of 12 liters. So since I have 9 liters of 50%, X is 9, and then 12 minus 9 would give me the 3 liters. Right? Because together 9 and 3 are going to add up to the 12 liters that I want. And depending on the problem, it might, what I solved for might not really like answer the problem. If someone said the question was, well, how much of the 50% and how much of the 10% should you mix? And if you just answered 9, they would say, what? Right? Like, what? That's not, let me ask that question again, right? So instead, you would then answer, well, 9 liters of the 50% and 3 liters of the 10%. And they would say, oh, okay, I get it now. Right. So it's like a conversation. You want to make sure that you're answering the question in a way that makes sense with how the question was asked. So again, a number of the application problems are going to be easier than the mixture problems just because they don't have this kind of slightly more complicated mixture equation in them. But they are all going to benefit from attacking them using the same kind of 5 steps here. Understand the problem, define the variable, find an equation, then you solve the equation, and then finally make sure that you answer the question and check your work. Okay, so when you're doing this work, just really practice working through those steps. They are going to help you. The goal of the problems is partly to get the right answer, but a lot of it is actually to work with these strategies that are going to help us when we see even more complicated problems. So in the beginning, some of the problems you might just be able to solve by kind of guessing. That's okay, but that's not what we're looking for in the work, right? Because we're preparing ourselves for some bigger and better problems and equations. Okay. So it was good because we did some problem solving there. We solved some equations. We talked at least briefly about kind of percents. We did not get a chance to talk about inequalities, linear and compound inequalities. So I'll definitely talk about those next Wednesday, but you'll want to make sure that you've tried those sections before our session so that you know kind of where any problems might lie with those. As will be the case throughout our course, this is no way like a comprehensive lecture, right? I just have, an hour, a little less than an hour. So I'm only able to kind of touch on some of the kind of most important points and make sure that I'm answering your questions. So you're going to need to go look at those little videos to make sure you're getting the instruction for the other topics. I don't feel like I've gotten a whole lot of questions from this class. And that's possible just because, you know, we've kind of taken a slow start to the course. I'm sure that the questions will pick up over the next week as you start to get closer to that due date. I will say again, and I'll post an announcement too, I won't be in email contact over the weekend. So from kind of Friday afternoon to Monday morning, I won't be able, most likely I won't be able to get back to you. Please continue to ask questions, but I'll answer them as soon as I get back on Monday for you. But just in case you're hoping for a quick response, I can't promise it this weekend. Okay, so